Okay, so last time we started to work on the heat equation here. So take some time to really look at it and get all the parts. You know, PDEs, just to understand the problem, requires a lot of technical knowledge. Just when you look at the problem to really see what you're looking at. So we've got the PDE here. And look at the domain. Then we've got the boundary condition. Think about when we say boundary condition, here we're substituting values for the spatial variable x. So these are conditions, you know, about what's happening to the rod, in this case at the left and right end. And in this case, we have homogeneous boundary conditions or trivial boundary conditions. The temperature is fixed at 0 on the left and right end, just for this, you know, kind of canonical problem. This is a fundamental problem here. It's the kind of ground floor. And then we have the so-called initial condition. And again, it's really important to go, okay, what's the difference between a boundary condition and initial condition? Here, we're replacing the time variable with a constant. So traditionally, we know the starting temperature. So this is f of x is the initial temperature distribution of the rod in our physical interpretation of these mathematical equations. So I mentioned this before, I just want to mention it again, you know, because this is new stuff. Traditionally, in any time you're generally working with a PDE like this, you know, you would traditionally, we would start by assuming that the solution we're looking for, which is the temperature at any point x along the rod and at any time t greater than 0, that it's made up of what we call this, you know, steady state solution, which is the long time solution, the asymptotic, which is n t to infinity, plus the so-called transient solution. And so how would we use this, this assumption? And so on the lecture for Monday, there'll be an example on those slides, and I'll post those today. But the idea is, just from a mathematical point of view, the way we would use this assumption now, and so I want you to think this through with me, is we would replace the u up here with this expression u bar plus v, and that would get plugged in right here for you. And, you know, because u is a function of, u bar is a function of one variable only, we could decompose this. We can use the linearity of derivatives. You know, the derivative of a sum is sum of the derivatives. We can decompose this into a PDE and a ODE. ODE for u bar, which, you know, partial u bar, partial t will be 0. So that ODE will be the one we solve to find the steady state solution. And then there'll be a PDE in V. And for that PDE, we will need a boundary condition and an initial condition. And we can use what's given to find that. Because once again, I can substitute in here, here for u, I can substitute in u bar plus v and use that to find boundary conditions. And again, for the initial condition, I can substitute right in here. I can substitute in this equation here, where the t would be 0, and find an initial condition. So that's what we would traditionally do. And, you know, I'll show you an example of that next time. But here in this case, the reason I'm not doing all of that is because in this case, because of the boundary conditions, the steady state solution is trivial. So here, you know, if we let u equal u bar plus v, well, u bar is just 0. Here, I'd just be replacing u with v. I'd just be playing this kind of silly game with the variables, u instead of v. So, okay, so I hope, you know, and what I've said will make more sense when we also talk about it next time, when I do actually use this approach, where I'll assume the temperature, you know, has this structure where it's the steady state solution plus the transient solution. Okay, so in this case, this steady state solution is trivial, is 0. So I'm just going to apply separation of variables directly to u of xt. What does that mean, apply separation of variables directly to u of xt? It means I assume u of xt is f times g and that it's non-trivial, and you plug in for u. So this is a procedure you'll be expected to mimic, and you'll see it on the homework that I'll post today, homework 5. And certainly, you should refer back to these slides as you kind of go through the process. And we'll be doing this process many times. So once we decompose the left and right hand side, so here, partial u partial t of f times g of t, the t derivative just goes to the g variable. And on the other side, we're taking, two partials with respect to x. Well, if you write u of xt as f of x times g of t, f is the only function that's a function of x. So that x derivative just goes on the f function. And now we do our separation of variables. So what that means is I want all my functions of x on one side and all my functions of t on the other side. And I'm going to go ahead and move k over as well. And so here on the other side, you can see I've separated my variables into t and x. And now so up until now, just basically, some basic properties of derivatives and algebra. So now we do a little bit of analysis. Here we can show the only way a function of t can equal a function of x is if they're both constants. And so, first of all, appreciate that part of it, that on one side here, I have a function of t, on the other side, it's a function of x, and those are, time and space, right? So here, what we do is we just show that we take the t derivative of the expression on the left-hand side, but then we say, wait a second, the thing we're taking the derivative of is the same as f double prime of x over f prime of x. So let me just put that in. And now I know the t derivative of a function of x will be 0. So the t derivative of this original left-hand side here, just supposed to be a function of t, its t derivative is 0, so it's a constant. Similarly, the x derivative of the right-hand side is 0, so it's a constant. So we're going to set them both equal to negative lambda, where lambda is some constant, and we introduce the minus sign for mathematical convenience for later on, because this is not the first time we're solving this problem, right? This is a famous thing we're doing here. So at the end, it'll make more sense with our intuition, and lambda will, that will be called an eigenvalue. Okay. So now we have two ODEs, and we've essentially, decoupled or, taken apart the original PDE in two variables. You now see we've decomposed it or decoupled it to these two ODEs. And so now the plan moving forward is to solve each one of these separately and then combine the solutions into what we call a product solution. And then to use the vector space theory, which says, if you have more than one solution, then any linear combination of that will again be a solution. And here, once we've solved both equations and combined them, we'll have more than one solution. We'll have infinitely many linearly independent solutions, okay? So we solve that what's so-called time domain problem, or the t variable problem. So here is g prime of t equals minus lambda k g of t, and be sure you know where we got this equation from. And it's on the previous slide. And so now we do the ODE technique of separation of variables, which is what? I put all the t variables together. So this g of t, I'm going to move to the other side and then integrate both sides. The integral of g prime over g is the natural log. Integral minus lambda k is minus lambda k t plus c, right? So this is our time variable. And so then I exponentiate both sides and account for the absolute value in the constant. So yeah, we get our time domain solution. And here there's no issue. It looks like there's just this one solution because it's a, it's a first order ODE. So there's no problem. There's just this one solution. So when we solve the X variable problem, we'll see that it's not that simple. So here, based on this solution, we expect lambda to be greater than 0 to be the only physically viable case, because we expect the temperature to decay, in this case, to 0, because the steady state solution is 0. So for this particular case, we expect as t goes to infinity that the temperature will go to 0. And here, this would work out perfect here. If the time component goes to 0, that'll force the temperature to go to 0 in a very natural way. So now we're going to use the boundary conditions and formulate the X variable problem, or the boundary variable problem, or also called the eigenvalue problem. So here we have to use the fact that, we're assuming u of xt is not trivial. So observe here, remember u of xt, this is equal to f of x times g. And so here I'm assuming the x variable is 0 because we're using the boundary condition. So here, this x right here in the f function, I've replaced with 0. And now, there's two options. F of 0 is equal to 0, g of t is equal to 0, or both. And so here we claim that the only possibility is f of 0 is equal to 0, because if g of t is equal to 0, then we have a trivial solution, and we're not allowing trivial solutions. Similarly, the boundary condition at the left end, we translate to a boundary condition on the function capital F. And so the X variable problem, or the boundary value problem, also called the eigenvalue problem, is formulated as, we've got f double prime equals minus lambda f of x. So again, I want you to make sure you know where we got this equation from. And then the boundary conditions are the ones we just got right here. So, you remember when we do our separation of variables, we set this thing equal to a constant. And so if we solve this equation, we'll get our X variable problem, or boundary value problem. And if we solve that, we get our time domain problem, right? So, okay. So now let's solve this. Look at it, it's a second order homogeneous ODE with homogeneous boundary conditions. Okay. So here, basically inspired by the first order solution, you look at the solution here, just from a mathematical point of view, this first order ODE, the solution is e raised to some constant times the variable. So just inspired by that form mathematically, we're going to assume in this case, the solution looks like e raised to a constant times x. Are there other solutions possible? Certainly, it's just we have to start somewhere. So r is a constant to be determined. So here, starting with the ODE, so now I want you to think about how we're going to use this assumption. E to the Rx, I'm plugging in. And so then that gives us this equation r squared e to the rx equals minus lambda e to the rx, and then e to the rx we cancel because, as you know, the exponential function is always, non-negative. So I get r squared equals minus lambda. And so this is called the characteristic polynomial. And here, we now want to solve for r squared. So what we do now is we approach this by cases. It's a very mathematical thing to do, right? So first we say, okay, what if lambda is less than 0? Then we say, okay, what if lambda is equal to 0, and what if lambda is greater than 0? And remember, we're looking for non-trivial answers, right? So what happens is, in 2 of these cases, we get trivial solutions. So like, suppose lambda equals 0, right? Consider this case. If lambda equals 0, then r squared is 0. And so we have a repeated root. So I don't know if you remember what we do when I have a repeated root, because this is a second order ODE. We're looking for 2 solutions, 2 linearly independent solutions. Okay, so in that case, we assume that f of x. So here I need 2 solutions. One solution is a constant, and we call it a. And now I need a second solution that's linearly independent. So we multiply it by x. We assume a solution of this form. And you can prove that you get a trivial solution in that case using the boundary conditions, because the boundary conditions are trivial. So the only way everything zeroes out is if all the coefficients are 0. In the case that lambda is negative, I will suggest, so in the case that lambda is negative, from just a math technical point of view, in the case that lambda is negative, I would write r squared as, for example, negative m squared, where m is, a real number. This way, so this would be my lambda. I would let this equal lambda, just from a math technical point of view, so I can do the math. That way, this forces it to always be negative, and then plug that in for r, or well, plug that in for r, and look at the well, you're gonna take the square root here. Remember that this is r squared. You're going to take the square root, but remember this negative m squared, that's not negative. That's actually, you'll get, I'll let you look at that. But yeah, so you do get trivial solutions in the case lambda is less than or equal to 0. Also, Haberman does it, so I'll let you look at that. So I want to focus on the case where we have non-trivial solutions, where you actually, we have something we can work with. Okay. All right, here we go. So if lambda is greater than 0, and this is where we bring the waves in. Okay, so I want you to keep in mind that, part of what Fourier is doing here is to try and solve these equations using cosine and sine, because the Fourier basis is really nice. Because we talked about the orthogonality is really nice, and it's continuous and differentiable and all that good stuff. Okay. So here, if lambda is greater than 0, negative lambda will be negative. So when we take the square root here, we're going to get imaginary numbers. So here, remember, square root of -1 is defined to be I. And so here we have the 2 roots plus minus I square root of lambda, where remember lambda is a positive number, so this is just a real number. And this is the imaginary part. So now I plug that in for R. So we have two roots, right? R1 and R2. And I'm plugging in for those roots here. So remember, our solution is assumed to be e to the Rx, and I have a R1 and a R2. Okay. Second order, you know, so two roots here. And so we reviewed, you know, in the review, we talked about Euler's formula. So Euler's formula, if you remember, says e to the I theta equals cosine theta plus I sine theta. Okay. Oh my God, writing, why? Okay. Now let's keep it going because it's Friday. How do we prove Euler's formula? Euler's formula starts with the max series for e to the x, which is x to the n over n factorial. Why am I doing this? Because, you know, let's just not accept the formula. Rage against the wind or something. So here, what you do is if you replace the x right here with I theta, and then you expand that out, you'll see that every other term is going to be constant. Oh, damn, Zoom. Sorry, folks. Zoom's messing. Okay. So yeah, when you plug that in, you do the powers, because I squared is -1, you know, I cubed again will be minus I to the fourth will be, you know, a real number. So every other number will be complex and you know, it'll alternate between real and complex numbers. So if you collect all the reals together and all the complex terms, you'll get the max series for cosine and sine. And so we get Euler's formula. It's a beautiful thing. And so here I'm using Euler's formula where theta now is, you know, lambda x. So cosine lambda x, I sine lambda x. And here we use the fact that sine is an odd function. So for the second term, I put in a minus lambda x, but cosine of minus x equals x. So I just dropped the minus sign. Why am I so obsessed with the writing? And then sine of minus lambda x right here. You know, sine is an odd function, so you can pull it out. I won't write that because y'all know that sine is an odd function and there's absolutely no reason for me to write it. So yeah. So now these are great solutions, but they involve imaginary numbers. And so we don't want the imaginary numbers. I don't want I involved. I would like to come up with, you know, a real solution. So now here comes some vector space theory, people. So this is it. Get ready. Let's get our vectors on. Okay, so here we go. So the vector space theory tells us, so the ODE is second order. So its solution space is dimension 2. So that means it has a basis of 2 vectors that are linearly independent. And that's what we found. Here's basis vector number 1, and here's basis vector number 2. And they're linearly independent, and they, you know, they span the solution space. Every solution can be written as a linear combination of these 2. But vector space theory tells us the basis is not unique. What's unique is the number of basis elements. Any 2 vectors in the space that are linearly independent will also form a basis for the solution space of this ODE. I'm going to say that again, folks. Since this is a 2-dimensional solution space, due to the fact that we have a second order homogeneous ODE, any two vectors that are linearly independent in the solution space will also form a basis. And now, so let's find two other linearly independent vectors in the solution space. So here's more vector space theory. Because the solution space is a vector space, any linear combination of solutions is again a solution. So what I'm going to do is I'm going to add this solution, e to the I square root lambda x. I'm going to add that to the other solution, e to the minus I square root lambda x. I'm going to add the Euler's formula version. I'm going to add them together. When you add them together, the sine, the sine function here cancels out. This sine function cancels out when you add them. The cosine functions double up. I get 2 cosine lambda x, and then so I divide by 2. And so here I find here, according to our vector space theory, this is also a solution because it's a linear combination of solutions. And now for the other solution, I subtract. So once again, I'm going to do, e to the I lambda x, the Euler's version of it, minus e to the minus I lambda x. And now when you subtract, the cosines cancel and you get negative 2i. So here, be careful. There's this complex number here. And it's positive 2i, not negative 2i. So I'm subtracting this term minus this term. So the two minuses cancel and it doubles up. You get 2i sine root lambda x. I divide by 2i. So here, remember, this becomes a plus when we subtract. So I divide by 2i, I get sine lambda x. So according to our vector space theory now, cosine root lambda x and sine root lambda x, since they're linearly independent, I'll let you think about why they're linearly independent. So you can the Wronskian's not 0, right? Since they're linearly independent and they're in the solution space and there's 2 of them, they also form a basis of the solution of the ODE, the boundary value problem, the X variable problem. And now superposition says here for the ODEs, superposition says any linear combination of these solutions is again a solution. So here we formulate this kind of generic solution of the X variable problem as a linear combination of cosine root lambda x and sine root lambda x. And keep in mind, we still haven't used the boundary conditions. So now we want to use the boundary conditions to to solve for lambda. And so here's where something crazy happens. Okay, so here I want you to really watch the subtle little thing that happens that makes this totally different from ODEs. Because cosine and sine are periodic functions, when we try to apply the boundary conditions, you know how periodic functions are. They have infinitely many solutions. And so here, when we try to apply the boundary conditions, because of the nature of these periodic functions, we will end up getting infinitely many solutions. And this is how a PDE is different from an ODE. This is a second order homogeneous PDE, but here we're about to show you that it has infinitely many solutions. Where second order homogeneous ODE had a dimension space, the dimension of the solution space is 2. So, okay, let's use the first boundary condition. So we have this trivial boundary condition on the left-hand side, f of 0 equals 0. And so go slowly here. So this x right here, oops, sorry, do that again. Evan, do you have one?
Yeah, so are you saying there's an infinite number of solutions or that the solution space is infinite dimensional?
Both. So here now, I stick a f of 0 in here, set this equal to 0, put a 0 in here, 0 in here. Alana?
If the solution space is infinite dimensional, how can it be spanned by just two functions?
The solution space of the ODE is spanned by two functions. The solution space of the PDE is not.
Okay.
So here we're gonna, so cosine of 0 is 1. So sine of 0 is 0, so this goes away. Sine of 0 is 0. Cosine of 0 is 1, as you remember, right? This is a 1. I'll just cross that out. So we get C1 equals 0. So this term is not here in our solution. The first boundary condition wipes out the cosine term. Now I want you to pay attention here. Just try and step back for 1 second and look at the big picture. By manipulating the boundary condition, we may be able to make one function or the other disappear. Like if the boundary condition instead of f of 0 equal to 0 was f prime of 0 equals 0, then that would make C2 equal to 0. Because when you take a derivative, you get C1 times sine, a negative sign, plus C2 times cosine. So, okay, so but don't worry about that too much. But here, by manipulating the boundary conditions here, we can make one term or the other potentially disappear. So now the other boundary condition. And okay, and so think about where the lambda is only here because we're solving a PDE. There wouldn't be a lambda here if we were just solving an ODE. The lambda is here because we started this with a PDE, okay? So here, when we let x equal L, so now x equals L. So here, put an L in right here. So there's a, so this term's not even here. So ignore that term and put an L in right here. So I get this. And on the other side here, there's a capital L here, and the boundary condition here is trivial. So I have C2 sine root lambda capital L equals 0. And now we're just doing trigonometry now. This is just, I told you, you use every math you learned, right? This is back to just trigonometry. Where is sine 0? So think about your unit circle. We didn't review unit circle, did we? Think about your unit circle. Sine is 0 at every integer value of pi, right? 0, pi, 2 pi. So 0 plus or minus pi, plus or minus 2 pi at every integer value. So it's root lambda L must equal n pi, where n is 0, plus minus 1, plus minus 2. And here I'm going to, L is a constant. I'm going to divide by L to isolate the square root of lambda. And then I'm going to square both sides. And so now I know what the eigenvalue. So this is the value of the eigenvalues. And you can see there's more than one. So here, and sorry, 0 is not included, because if you let n equals 0 be included, then lambda equals 0, it will be our eigenvalue. And in this case, we have a trivial solution, which you can show that. So that's why here 0 is not included, because lambda equal to 0 gives us a trivial solution. Okay. If n equals 0, then lambda equals 0. But we said in an earlier slide, lambda equals 0 yields a trivial solution. So we're not allowing that. So we have the value of the eigenvalue. And if you plug in here for square root of lambda, right here, and then go back to the x variable, we get the solutions here of this boundary value problem of the heat equation PDE. And this boundary value problem of the heat equation PDE has infinitely many solutions. Oh, and here I dropped the negative roots because we only want the solutions that are linearly independent. And here, sine of negative x equals negative sine of x. So sine of negative x is just a scalar multiple of sine of x. So here, I drop the negative roots because they're redundant. So you can just pull the minus sign out, absorb it into the constant, and say it's just a multiple of, you know, the one with the, I could have dropped the positive roots, but, you know, why be difficult? Evan.
So each eigenvalue gives us a different basis for a solution space, right? That's where the infinite bases come from. Okay, got it. Thank you.
Yes, you're right on. You're right on. So here, you know, so we've done most of the heavy lifting. So if you're, you know, and this is a procedure, obviously you should review a bunch of times and go over the little details that I didn't write down, like the vector space theory, you know, and of course I'll post the recording of the lecture this afternoon. It's the little vector space theory stuff that when you're in the middle of doing the problem, there's so much going on, you kind of sometimes will get disoriented and be like, wait, what's going on? So it either helps to review a couple of times, or if you could teach matrix methods like 6 times, that's what I did. That really helps a lot. But yeah, just go slow. The actual math is not hard. It's the vector space theory that allows us to stitch the solutions together. That's what's tricky. So now watch. Now we have the time domain problem. We have the X domain problem. So look, I really want you to pay attention to what happened to lambda here when we solved the boundary value problem. It turns out there isn't one lambda, there's infinitely many. Lambda sub n. So what? Well, if we go back to the time domain problem, this lambda here now, because of the developments in the boundary value problem, this lambda here now has been replaced with a lambda sub n. This is now going to be a lambda sub n from what happened on the previous slide, because we found the eigenvalues, and you know, there's infinitely many of them. The eigenvalues, just to remind you again, these are the eigenvalues. I mean, it's being squared, so the negative doesn't really matter, right? But those are the eigenvalues. So now we have to create the product solution. So we're going back to our separation of variables assumption, which said I assumed U was F times G. But at that point, I was just assuming there was one solution. Now it turns out there's infinitely many solutions. So now I'm saying U sub n is F of n times G sub n, where for each n, that's a solution. That's a product solution. And here, look, I replaced the lambda here with lambda sub n, because the time domain problem solution was like e to the minus whatever lambda kt. Now it's lambda sub n kt. And here is my spatial, you know. So one part is taking care of space and one part is taking care of time. And each of these functions is a solution. Theoretically, we haven't verified anything. Theoretically. So now, here's the other, you know, again, vector space theory kicks in. I don't want to have infinity many solutions dangling on my keychain when I try to walk around. I want one solution, all tied up neatly, right? Just give me one solution. So principal superposition says, we know the solution space here, set of functions that satisfy the PDE. Now I'm talking about the PDE. Up until this point, every time I talk about superposition or something like that, or vector space theory, we were talking about ODEs. So now I'm saying the set of functions that satisfy the PDE and the boundary conditions of the PDE, but not the initial conditions. We bring the initial conditions in last, ironically. That forms a vector space. And so what that means is any linear combination of solutions is again a solution. So now what I'm going to do is make an infinite linear combination of these infinitely many solutions. Here it is, my big mega linear combination of all infinitely many solutions. It's not a Fourier series. Pump your brakes. Don't get too excited. But there's a Fourier series lurking in there. If we let t equal 0, then the exponential term disappears. And then, aha, it starts to look like a Fourier series if we let t equal to 0. And why would we let t equal to 0 at the very end here to enforce the initial condition? Okay, so be careful. This right here is not a Fourier series. I mean, some, in the book or maybe in the homework problems, I might loosely refer to it as a Fourier series, but it technically is not a Fourier. So this would be the series representation of the solution of the, the solution to the PDE and the boundary conditions. We still haven't solved the initial condition. Okay, so it's not technically a Fourier series, but now we're going to let t equal to 0. So here, let t equal to 0 for the initial condition, right? Time is 0, initial condition. Here, when you let t equal to 0, we all know e to the 0 is just 1. Then you're going to get a Fourier series. It's not the full Fourier series. It's a Fourier series involving only the sine terms. And if you remember when you did the homework, I made you show all the Fourier bases were orthogonal in steps, actually. I made you first show, just the cosines by themselves are orthogonal. The sines by themselves are orthogonal. The sines and cosines are orthogonal. The sines and cosines with constants are orthogonal. So we can actually have the Fourier series, we can repeat it kind of just using the sine functions. So we can treat just the sines by themselves as an orthogonal basis, and we can create what's called a Fourier sine series. Evan. Did you have a question, Evan? I can't hear you.
Sorry, yeah, my internet's breaking up. So what was the motivation behind going from lowercase beta n to uppercase beta n?
Just because I'm now technically taking a linear combination of those other solutions. So I'm multiplying those solutions by another constant.
Okay, got it. Thank you.
I'm taking a linear combination of something. It's only like this super nerdy thing that a guy like me would like keep track of. You know what I'm saying? Like I'm keeping track of the constants being multiplied to the constants, but it helps me sleep at night. So that's what I got to do. So yeah, thank you for that question, by the way. Just so you know, all of the machinery that's happening in the background that I'm trying to keep track of also, so yeah. So now think about this, folks. This is not a full Fourier series. I want you to really, this part's a little tricky and I might go over like by 2 minutes, but it's really important for me to get this straight. When we looked at a regular Fourier series, think about this. We looked at the interval minus L to L. In this case, that's not what I have. I do not have the interval minus L to L. I have the interval 0 to L. So this isn't exactly the case we studied. Okay, but it's very similar. We can do all the theory we've done, just restricted to the sine basis, because just the sine functions by themselves are orthogonal. Okay, so here when we impose the initial condition, we get our initial temperature f of x is equal to this Fourier sine series. And now you can use the orthogonality. You can multiply both sides here by sine of, m, sine of m pi xl to both sides. Multiply that to both sides and integrate. Because of orthogonality, the only one that'll survive is when you have a sine of m here. That'll be the only one that survives. And then you can isolate the b sub n. And so this is all math you've done in the first couple of weeks, and you know how to do this. You just have to know that you know it. It's from the orthogonality. You can create a projection formula just for the sine functions. And so here, once we've used orthogonality to find the Fourier, the coefficients, the Fourier coefficients, using the initial condition, that's the other thing I don't want you to, this is where the initial condition at the very end has finally kicked in. And when we let t equal to 0, this series solution that we created does now look like a bona fide type of Fourier series. It's not the type of Fourier series that we're comfortable with, that we studied, that are on minus L to L. It's the type of Fourier series that's defined on 0 to L. It's very similar. We'll talk about what its properties and behavior, what it is exactly in a hot minute here. But here's our solution, our formal solution. We haven't verified it. So this is our mathematical formal solution that we've cobbled together. We've mathematically created this thing to satisfy every part of the problem. It'll satisfy the initial condition. It'll satisfy the PDE. It'll satisfy the boundary conditions. We mathematically created it to do that because we took a backwards approach. We took this generic solution and tailor fitted it to this situation.
Dr. Bott?
Yes, sir.
For our f of x and our integral here,
Yeah.
so we don't have an analytic version of it because it's an infinite sum, correct?
That's right.
Okay.
So now our theory says if f of x is piecewise smooth or continuous, we'll know that it converges on the boundary. I still need to discuss the convergence of the overall solution, which is not a Fourier series. I still need to discuss the convergence of the bigger solution. But one thing we have working in our favor is this exponential term is decaying to 0, and it's going to 0 very, very fast. And so we'll be able to, when f of x is a continuous or piecewise smooth function, we'll be able to show that you have very strong convergence of this type of solution. And that's what I'll talk about on Monday.
Gotcha. Thank you.
So the only final thing left to talk about, which I'll finish up on Monday here, we've gotten through separation of variables, everybody. The discussion we've had up through now, this is exactly, the core stuff of what we've been preparing for, this procedure right here. And we've solved a PDE. Well, assuming convergence, and we need to verify the solution. So many caveats, right? In math and PDEs, that's how life is. We can, I'll just tell you, yeah, this will verify the solution and it'll converge. So at least you can go to bed tonight, with have a good sleep. So only thing left to round out this particular lecture, which I'll pick up on Monday, which I want you to read ahead, is the math of a Fourier sine series. So now nothing to do with the PDE, particularly, necessarily, just what is a Fourier sine series and how do we interpret it? Okay, so I'll talk about odd extensions and I'll talk about what a Fourier sine series is and how it relates to a regular Fourier series next time. And I'll also talk about the convergence. So I'll post the lecture for Monday ahead of time if you want to read ahead. But you should definitely be able to do 2 of the 3 problems for homework number 5 right away, today once they're posted. All right, everybody, I thank you for your time and patience. So I'm going to stop right here. I ran a little bit over and I really thank you for your time. All right, so I'm going to stop right here.